This video is going to be the first of many on IoT programming, and as it's the first video, we're going to be touching on the fundamentals of IoT, with each lesson building up with more practical demonstrations and more complex theory. So to start with, what is IoT? So just an overview. An IoT is a network of physical objects, things embedded with electronics that sense, collect, and exchange data over the internet. The modern scope is that it expands beyond traditional electronics to include smart tagged non-electrical entities such as food, clothing, livestock, and infrastructure. So the formula for IoT is a regular object plus microprocessors slash sensors plus internet connectivity equals to IoT device. For example, a standard wristwatch becomes a smartwatch. The core value is that it uses interconnected data from billions of machines to automate daily life and optimize decisions across health, transit, and home environments. IoT market trends and adoption rates. So we've seen explosive device growth. So pre-2010, legally crossed the threshold where total connected devices surpassed the global human population. Today, in 2026, we've reached around 21.9 billion active endpoints globally. Legacy predictions expected 100 billion plus by now, which has turned out to just be early industry hype. However, projected to reach 47.1 billion in 5 years' time, as 5G, massive machine type communication, and smart automation stabilize globally. Now we look at data and market value. So a nascent, highly fragmented ecosystem worth under 100 billion pre-2010, but today in 2026 is valued at 1.1 trillion as enterprise digital transformations scale up. Legacy reports again estimated a 14.7 trillion market by 2022, so 4 years ago, which was significantly over budgeted. However, in 5 years' time, it is projected to increase again to around 4.2 trillion due to heavy adoption of hardware as a service models and Industry 4.0 infrastructure. Per capita adoption surge. So pre-2010, there was average fewer than one connected device per person globally. However, today in 2026, we're averaging strictly against global population sits at approximately 4 to 5 devices per person. However, hyperconnected smart homes now average around 33 active devices per household. In 5 years' time, expected to rise to an average of 6 devices per person globally, driven by a surge in consumer wearables and low-cost smart tracking assets. Macro drivers and ecosystem convergence. So macro drivers are driven heavily by rapid urbanization, with 70% of the world's population expected to live in cities by 2050, occupying 2% of land but consuming 75% of resources. Tech convergence, IoT adoption is moving towards 80 to 95% by 2030, heavily integrated with parallel technologies like AI, blockchain, and augmented reality, as well as expanding application ecosystem. Ecosystem has evolved from basic tech to smart homes, wearable, health, fitness, lifestyle, cooking, pets, gardening, and massive industrial sectors, infrastructure, robotics, retail, and green tech. So an introduction to IoT architecture. The core language that we're going to be looking at is Arduino IDE programming, which is primarily based on C/C++. Python is also used as a foundational language for high-level tasks, e.g. edge processing. End-to-end architecture, a bidirectional two-way flow of data where information moves from left to right, sensors to network to platform to application to customer, and control/commands flow back from right to left, customer back down to sensors in that process that we discussed. So what is IDE? IDE stands for an integrated development environment. It's the software that consolidates essential tools for programming into single application, enhancing productivity and streamlining the development process. Core features typically include a code editor, which provides syntax highlighting, auto completion, and error detection to make writing code easier and more efficient. We have compiler/interpreter, which converts human readable code into machine executable instructions. We have a debugger, which helps identify and fix errors in the code by providing detailed feedback and breakpoints. Build automation, which automates compiling, linking, and packaging of software. We have version control integration, which supports tools like Git to track changes and manage collaborative development. And we have extension and plugins, which allows customization to support for multiple programming languages. IDEs can be desktop-based, web-based, or mobile-based, and some modern IDEs incorporate AI assistants to suggest code, analyze bugs, and even implement solutions. This diagram that we're going to be looking at now just illustrates the bidirectional flow of an IoT solution, showing how raw data travels from local device sensors to network and platform providers to application layers like smart cities and transport before ultimately reaching the end customer. Moving on to technical building blocks, we have the hardware, software, and sensor nodes. So a sensor node is a physical sensing device equipped with built-in processing and communication capabilities. The IoT formula is, like we touched on before, regular sensor plus processor, for example, Arduino, plus connectivity, which will equal to IoT sensor/device. Communication protocols, hardware components interact primarily through serial communication, for example, sensors connecting to the microcontroller, which in turn connects to the networking modules. Edge computing and networking. We have edge servers, which are intermediate devices positioned between the local sensor nodes and the cloud to process data closer to the source, reducing latency and bandwidth. Network diversity. IoT solutions leverage a wide variety of communication networks depending on range and power requirements, including Wi-Fi, Zigbee, Sigfox, Bluetooth, and cellular mobile networks. Protocols are strictly defined communication standards that So languages, for instance, that devices must follow to successfully establish a connection and exchange data. Cloud convergence and architecture. So the benefits of cloud is that in centralizing resources in cloud eliminates the need for expensive on-site software and hardware infrastructure, facilitating global data distribution. Architectural models. Systems are designed using service-oriented and API-based architectures to streamline machine integration. Semantic sensor networks, an ontological framework tracking a source thing, a stimulus trigger, and a sensor that records events. It attaches meaning, context like time, location to raw readings to turn data into actionable insight. This second diagram demonstrates the physical components required to build a functional IoT sensor node by linking individual sensors to microcontroller boards such as Arduino or ESP32 and wireless connectivity modules via serial communication. Data management and analytics, the big data scale. So this is just for a idea of how much data is being inputted and utilized in today. So weekly rig generation, a single offshore oil rig generates 500 gigabits of data per week. Daily sensor yield is 101 billion distinct data points captured globally every day. Industrial scale, an oil refinery generates 1,000 gigabits daily. A single jet engine generates 10,000 gigabits every 32 minutes, or 30 minutes, sorry. Global output, 2.5 billion gigabytes, 2.5 exabytes are created worldwide daily. And here's the fact that really stuck out for me. 90% of the world's total data was created in just the last 2 years. So that exponential growth is only just going to continue. Data versus information, the structure problem. 90% of collected IoT data is unstructured, raw, while only 10% arrives structured. The translation is that raw data points, e.g. a constant stream of heart rates like 80, 90, 85, hold little value until analytics extract meaning to create information. For example, your heart rates are abnormally high compared to your usual running baseline. Security, privacy, and Industry 4.0. So the security challenge and why it's fundamental for cybersecurity students to at least touch on IoT programming is that IoT devices are highly vulnerable because they exist in massive quantities, sit physically close to users, possess weaker native security protection, and store highly personalized data. Industry 4.0 transformation, the global migration from automated production to completely integrated cyber-physical systems, where up to half of all manual industrial processes can be fully optimized and automated using IoT ecosystems. So the requirements over the weeks, so that you can follow along as well, because really this was a big theory dump, this first video, but it's going to get more practical over the next few weeks with more coding and physical setups using the Arduino kit. So to successfully complete the lab sessions for this unit, you'll need a physical Arduino kit as seen in this diagram here. You'll also need to download the Raspberry Pi OS operating system with this desktop version. And obviously I'm assuming that you would either have VMware or VirtualBox. I prefer VMware, but it's up to you, but you'd have to have this download as well to load the operating system onto. So alongside the physical hardware, you need a Raspberry Pi desktop operating system, inside a virtual hypervisor on your computer. Having both of these environments ready is critically important because they form the foundational hardware and software building blocks of a complete end-to-end IoT architecture. The physical Arduino kit allows you to learn local device programming, serial communication, and how to capture raw environmental data through sensor nodes. Meanwhile, the virtualized Raspberry Pi operating system serves as your edge and platform layer, enabling you to practice data management, network protocols, cloud convergence, and the high-level analytics required to turn raw sensor data into meaningful information. Thank you for watching this video. I'm super excited to get into this, and it's going to be a lot of fun, and hopefully you follow along in the future weeks. Thank you very much.